too complex. Let's kick things off. As usual, question, concept, solution. Welcome back to another video. We are going to be continuing with ventilation. If you haven't seen the first part of this video, please make sure to do so, because most of what we'll be talking about here will be a continuation of that. So as usual, we are going to start with the question, cover some concepts that we need to understand, and then we can then go to the solution. So a production section in your mind is supplied with a fresh air quantity of 54 cubic meters per second through an intake airway that is 3.4 meters high, 3.6 meters wide, and 400 meters long. The air density is 1.004 kilogram per cubic meters. Due to low grade, you plan to reduce the production in this section and therefore want to reduce the ventilation air quantity to 30 cubic meters per second. Assume a friction factor of 0.01 and s squared over m to the power 4. Calculate the area of the regulator to be used. Now, from the question, we can pick up several things. First of all, we are made aware that we are dealing with regulators. So regulators would be under what we call flow control structures. Okay, so under these flow control structures would have things like your stoppings, would have seals, would have doors and airlocks. We would have regulators, which is the focus of our video, and finally would have crossings. So what does a regulator do exactly? So the regulator, it limits the flow of air in an airway by absorbing some of the pressure. Okay, and this sounds theoretically great, but you would then ask, how do you do this practically? How do you absorb pressure, right, in an airway? Well, we do that by reducing the cross-sectional area. So essentially, it's a structure that you would put up in an airway to reduce the cross-sectional area, which absorbs the pressure, therefore limiting the flow of air. So that's what we are dealing with. So that's your regulator in perspective. As far as calculations are concerned, there isn't much content to discuss. However, what we need to know are the following equations. So the first equation you need to familiarize yourself with is A reg is equals to 1.2 Q, the root of density over the pressure. So just for extra stuff, the density is not actually P, it's a Greek letter called rho, R-H-O, and it's pronounced rho. So that's how you should call it from now on. So it's rho over P, not the P density over the P pressure. It's rho over P. Okay. So the rho is the density of air as established. It's kilogram per cubic meters, and then the P is the pressure. You need to understand this. It's a pressure required to be absorbed by the regulator. Not just any pressure. You don't just substitute any pressure into this equation. Okay, you need to understand what pressure you need to substitute. Okay, then you've got Q, which we've established already. That's the required quantity. Okay, a reg would be the area of your regulator. So from the previous video, we spoke about the formula of resistance as given by Atkinson. We spoke about the relationship between the pressure and the volumetric airflow, or the air quantity, as P is equals to RQ squared, right? But at the same time, we said that R can be calculated as KCL over A to the power 3 times rho over 1.2. So when we substitute this into P is equals to RQ squared, we can establish a separate formula for the calculation of pressure as KCL Q squared over A to the power 3 times rho over 1.2. These are the formulas we need to understand to deal with regulators. Back to the question. So to find the pressure absorbed, I'm going to call it P absorbed. This will be equals to P high minus P low. So higher pressure minus the lower pressure. Okay, so how do we calculate the pressure? So P is equals to KCL Q squared over A to the power 3 times rho over 1.2. So let's subscript the pressures to be able to distinguish them. So let's say P54. So that's going to be 0.01. Circumference going to be 2, 3.4 plus 3.6. Close that. 400 meters long times the air quantity 54 squared. Close that, divided by 3.4 times 3.6 to the power 3 times 1.004 over 1.2. Punch that. And we get 74.50471,538, and this is pascals. Do the same for P30. So it's gonna be 0.01, 2, 3.4 plus 3.6. Close that. 400. This time we have 30 squared all over 3.4 times 3.6 to the power 3 multiplied by 1.004 over 1.2. Punch that. Just gonna change the 54 to 30, and we get 22.99528252. This is pascals. P absorbed is going to be equal to P high 74.50471,538 minus 22.99528,252, and we get P absorbed 51.50943286 pascals. Okay, now we can substitute into the equation to find the area of the regulator. 1.2 30 1.004 over 51 point. By the way, the 30 there is the required. If you remember from the definition, you've got two quantities, you need to know which one to substitute. The one that is required, so you are reducing 2, that's the quantity you need to substitute. So continuing here, and we get 5.02604036376. So this we can round off to 5 meters squared. So that will be our answer. Note, there's a check here. If you say the area of the regulator over the area of the tunnel times 100, you will get a percentage. That percentage must not be greater than 10%. Why? Because this equation is only valid for the area of the regulator, not bigger than 10%. Okay, so what happens if it's somehow greater than 10%? Then you would want to install a temporary or an adjustable regulator to adjust it until you reach the desired flow. You don't want a permanent structure greater than 10%. And that is the end of this video. Too complex?